Can you see my slides?
Yes, we can.
Okay, so you just see the title slide. Good. Okay, so before I get to the research, I'd just like to thank my research group. So they make all of this great research possible, of course, and some funding sources. So in recent years, we have seen a convergence of material intelligence, biomechanics, and robophysical modeling. And this has enabled biomimetics in important ways. So here are a few areas that my group has contributed to. So are you just, you are seeing the slides well, right? You are seeing just the title slide, is that right?
We're seeing the slides correctly. Everything looks great.
The name of the session, of course, is Bio-Inspired Robotics. And I see two important approaches. So one is biomimetics, as we're become accustomed to, and the other is robotics-inspired biology. So my first experience in bio-inspired robotics came through a DARPA project starting in 2005. And there we worked on climbing robots, and this led to a discovery in biology. And so this was a profound experience for me. And I want to tell you a bit about this approach of how robots can be powerful to make a discovery in another field. So this was an amazing collaboration between 7 partners, including Boston Dynamics and of course UPenn, Stanford, and Berkeley. And the goal was to build a multi-legged climbing robot. And first it was insect-inspired, a hexapod, but increasingly it was found that a tail was important for climbing. And so this led the roboticists to ask what is known about tail use in nature. And so I noticed also in the poster session, we had a lot of different tail posters. So it was not always so obvious that tails are actually useful in animal locomotion. So when we looked at it, tails could have various uses. They could be used for communication, for fat storage, for many different functions that have nothing to do with locomotion. Here we wanted to look at how geckos, nature's elite climbers, use their tails for highly dynamic wall running. And so we tested this hypothesis that a tail reflex could help in within 50 milliseconds, say, to reject perturbations during climbing at 30 hertz. So this is a gecko you see in real time going vertically, and we embedded a slippery patch where front foot traction was removed. And so you saw within 30 milliseconds, they began to move the tail down incredibly fast. And then we measured the wall reaction forces, and we found tailless animals fell more frequently. And we found that the stabilizing impulse moment was actually matching what the front foot that is perturbed would normally generate. And so this led us to get back to rise and add an active tail. And so the active tail helped with transitions from horizontal to vertical. And it also inspired a variety of other tail climbing robots, such as by Metin's group. So, however, if you look at the animal, it's using, actually, its body is soft, right? It's made predominantly of water. And these biorobotic models had actually been rigid before, mostly. Taking this further, more recently, we studied more compliant tails. So as you see here in A, the gecko is actually is able to generate an edge load more than a point load. So we started working with more compliant tails. And I'll skip here to the climbing test. So here in this very simple wedge-based climbing robot, you see we have a compliant tail. And so the compliant tail can actually help with obstacle traversal in different situations, but you would need to be able to have a stiffness control. And that's what we're working on most recently. Here we have also added a soft sensor and it can give us proprioceptive information of this fifth appendage. And we think of Gecko locomotion more as pentapedal now, as opposed to quadrupedal. So if you traverse two gaps, one after the other, a rigid tail could actually get in the way and inhibit locomotion. So a compliant tail can be helpful as you traverse multiple hurdles. So this is how we've expanded the study on contact tails, trying 4 different stiffnesses here in this fin ray-shaped legged robot. So in this study, we basically looked at the advantages of a flexible tail. We also looked at compliance in the neck, so a heads or tails study, which I don't have time to cover here. But just to give you a taste, basically the goal of this research is a biorobotics approach, as you may know from Professor Auke Isvert or from Lee Wen, Alex. So we use biorobotics to emulate and investigate animal locomotion before we transfer it to robotics. And of course, soft materials are the greatest difference between conventional robots and animals. And so we think it's a key to agility to incorporate material advances as they become available. So to this end, we have been using soft sensors, also in collaboration with Young-Lei Park, who spoke this morning. And we hope that this approach will help achieve more lifelike movement. So we have been using the soft strain sensors also not only in climbing, but also in swimming, which I hope I get to towards the end of the talk. But first, I want to speak also, we spoke earlier about arboreal locomotion and climbing. So any robot that climbs up has to eventually come down or have a plan for reorientation. And coming from UPenn, we had, of course, CKBot, and it's a modular robot that rides like the falling cat. And so what we found is that the Gecko does it very different from the falling cat, which uses mostly bending of the back. So the Gecko, when it comes from upside down to right side up, it uses a swing of its tail in one direction to cause a reorientation of the body in the other. And this is the fastest righting behavior yet observed. So angular momentum is conserved in roll as it falls. And we studied this carefully with also tailed and tailless experiments, which is important in biomechanics. So we built a 3D dynamic model and confirmed that inertia was sufficient to explain the righting behavior of the Gecko. So this inspired the righting response of StickyBot, which was presented in a TED Talk. So it was able to use with a simple spring released through a thread to reorient itself. And so we can change, we can do body attitude control, change orientation of the body by using tail inertia, which in lizards is 10% of body mass. And this doesn't only help in free fall. Free fall, of course, is a great experiment because no external forces are acting on the system except gravity. And so we wondered, how is that for rapid running? And so in this study, we tested vaulting or hurdle traversal of a sub-Saharan lizard. And we have 2 control experiments. So we have one with good traction, where it can use the ground reaction forces vector going through the center of mass to control flight and vaulting, or as it slips, this is what we found happens. So when the lizard slips on this box, it pitches its tail up, allowing it to maintain heading. And so you see, we tested this with the robotic model. So this is a very simple robot. We drive off a ramp to get a misalignment torque, and we temporarily redirect excess energy from the body to the tail to maintain heading. And so in the interest of time, I'll skip the details here. This is simple robot. We have PD control. But interestingly, you all are familiar with Mark Rober, right? So he perturbs squirrels with a feeder and a spring system where they get catapulted in an undesired body orientation. And so we studied the kinematics of how they rotate their tails to land on their paws. And so we also built a robot to explore this further. And so in this squirrel robot, you can see we have a bend servo, we have a microcontroller, battery, IMU, and so we can, as this robot is perturbed in the same fashion as the squirrel, you see here on the left side that the tail will rotate to arrest this undesired rotation in the body in rule. So we, of course, work with Amir Patel, who is of the African robotics unit on tail use in cheetahs. We have a nice review paper on this if you'd like to take a look at that. But of course, what Amir has found is that the cheetahs could also use the aerodynamic aspect of the tail. So drag torque of these cheetah tails, as opposed to predominantly inertia. So in free fall, inertia predominates in the geckos. However, what I've studied is also their gliding behavior in the wind tunnel. And so here you see a gecko filmed from the top down, and you have a vertical wind tunnel where essentially the aerodynamic forces balance the forces of gravity. So we have the equilibrium gliding. And our question first was, having found that lizards right themselves using tail inertia, we thought, okay, in a plane orthogonal to airflow, they could use also mostly inertia to turn in yaw. And so we tested if inertia alone was sufficient to explain motion perpendicular to flow. And using genetic algorithms, we explored different conical shapes that the animals are exhibiting. And we found also, using a robotic model, that aerodynamic forces as well as inertial forces are used at this scale for gliding. So then we, to find out whether these animals are able to land after gliding and glide in the rainforest at all, we went to Southeast Asia. And in the wildlife reserves of Singapore, I was able to film how they alight on a vertical tree trunk. And we found an incredible behavior. As you see there, they are able to pitch back 120 degrees from the vertical. And they use their tails for this fall arresting response. So we then built a robot, a soft robotic physical model of this gecko to study the landing dynamics, if you will. So using a catapult, we were able to launch the robot at a force plate, and we measured the forces on the rear foot required to land effectively. So you can see here that the tailless landing performance was dramatically reduced in the robot. This was also found for some tailless geckos that landed. So the back, the soft back, is very important in this behavior. It is actually printed on the carbon M2. And so as the robot approaches, we have a proximity sensor, and we are able to activate also an active tail response. But if you look at the bottom plot, so this effectively, you see relative tail length as a function of peak foot force. So why would tailless robots fall more frequently? Well, it's because forces required at the rear leg during the fall arresting response are inversely proportional to length of tail. So if you look at the maximum adhesion force of this gecko, modeling would suggest that the forces at the foot required to remain attached would be greater than the leg attachment maximum force. So Richard Feynman, the famous physicist, said, "What I cannot create, I do not understand." And so in biorobotics and bio-inspired robotics with conventional materials, we have not quite been able to close the gap between agility and robustness in animal locomotion. And I hope that with new approaches coming from soft actuators and soft sensors, we would be better able to understand these systems relationships. So to this end of achieving active stiffness control with soft robotic tails, we explore the body caudal fin swimming of fishes. So of course there have been many swimming robots, including of course of so we have Marchese and all. We have Suzumori had of course a swimming the first swimming robot that I know of. We have Rob Shepard, of course, with the embodied energy aspect. So our interest was in exploring how stiffness control could affect swimming performance. And to measure swimming performance, we attached our physical model to a force torque sensor and measured instantaneous thrust. So of course you would all know the dead trout video, where if it swims in a Van Karman vortex street, it's able to effectively have propulsion without muscle activation. So if you could do hydrodynamic tuning, right, it would be much more efficient. And so this is what we set out to explore. And we also used soft sensors working with Youngley to effectively close the loop in swimming. So in our latest work, we were able to control tail amplitude with a simple PID controller. We have also done a PIV. So what you see there is the soft robotic fish swimming in a flow tank, and you see the soft sensors and actuators on top. So what we found is that some stiffening and bilateral co-contraction resulted in the peak thrust, as was hypothesized in the fish swimming literature. So we also used a lump parameter model to estimate actuator dynamics. And so our input is air pressure, the output is tail displacement. And so the parameter values of the model were optimized with this genetic algorithm using real world data. So to sum up, we find that a key enabler of biomimicry is soft active materials in terms of sensors and fluidic actuators, but also additive manufacturing, of course. And this has allowed for very interesting new physical models for biomechanists also to test hypotheses of neuromechanics. So essentially, we can, equipped with these new technologies, we can do more robotics-inspired biology to better understand the morphological computation we find in nature, and it enables physical model-based experimental validation. So with that, I'd like to thank some funding agencies, including the Humboldt Foundation, Cyber Valley, and the Max Planck Institute. And please take a look at our research, which has been featured in the news media. Thank you very much.
Thank you, Ardian, so much for the talk. Does anybody have any questions? We have time for a couple. Yeah.
Yeah, thank you very much for the very interesting presentation. And I would be interested in actually the general topic that we have here, as in biomimetics versus biology inspired by robotics. That cycle that you put forth here, which is also described, as you said, by ICRA in 2014. And I always wonder, how do we actually start the cycle here? Because sometimes we don't even have a rudimentary understanding of how these biological processes actually work. So then building a robot from only minimal understanding could be quite difficult. So what could we then infer from a model that might be inherently wrong due to our initial biases maybe? So that's, yeah, how do we start the cycle actually? That would be the general question.
Well, I think it's both approaches are fine, whether you started from more experimental biomechanics or from experimental robotics. As I mentioned in the beginning, that some 17 years ago, right, the Dark Horizons project was an engineering project to build a climbing robot, and there it was found that through experimental robotics that the tail was helpful even if you have 6 legs. So even 2 or 3 of those can slip, still you needed the tail. That then inspired the question of looking more closely at the biomechanics of climbing. And so I think roboticists are ideally equipped to ask the next big questions. And then what a robot also gives you, of course, you control the input, you measure the output at higher precision than you can with animals. So you can explore a much greater parameter space and refine hypotheses of neuromechanics of locomotion. So this really puts us in a position to study and make discoveries of animal locomotion before we then go on to transfer them to engineering robotics and generate new capabilities for robust locomotion in robots. I don't know if that answers your question.
It actually does. Thank you very much. So an initial, rudimentary implementation might already get us somewhere. So yeah, that's very good to hear. Yeah. So thank you very much.
You're welcome.
Okay, any other questions? You're at a little bit of a disadvantage, Ardian, because you're the last speaker before lunch. I think
Oh, I see.
getting out of here.
People want to get to lunch. Okay. Yes. So I had another thought about this question, but I think it just slipped my mind in terms of. Well, I think generally that really robotics is increasingly required for expanding studies of biomechanics and neuromechanics. And then we of course see since the session is on bio-inspired design, right? We have different communities, sub-communities with different interests. And we have different levels of biomimicry, if you will, right? Some are very abstracted and removed from the model system, and some are much closer to copying, say, a particular structure like you have in the shark skin, right, that reduces drag. Yeah. So this would be an interesting topic to discuss in a panel discussion.
Yeah, no, that's a really good idea. And we'll think about it for future workshops or if there's time later in the day. Thank you so much for joining us, Ardian. It's great to see you.
Likewise. Thank you so much.
Okay. See you. Okay, we are going